Alrighty, I wanted to record some comments for you guys about these 5 problems. Um, I just want to highlight literally the fact that problem 20 and problem 20 and also problem 23, those were the 2 problems that asked you to prove that a certain set with a certain operation is a group. And that might be familiar to you from your days in abstract algebra class. But A, it's a very good thing to review because it really gets you thinking about the group axioms. And B, really, the group axioms are a part of K-12 algebra, right? I mean, that's part of what we're on about here, but also they're familiar to you. Like you're familiar with the idea of associativity as something that you might talk about with your students in your classroom. And also, inverses are something that underlie a lot of important algebraic properties. So, I just wanted to give you guys a chance to think about those 3 things: associativity, existence of an identity, and inverses. And I'm going to highlight some things that you may or may not have noticed or thought about, and that's what the feedback is for. So you can think about these things and think about whether your group's work kind of reflects these considerations. So, first of all, if you had a proof for associativity, then that just gets you thinking about what associativity actually says. And that's important because there tends to be some confusion about associativity versus commutativity sometimes. So even though we're not talking about commutativity yet because it's not part of the group axioms, we're going to come back to associativity when we talk about comparing it to commutativity and stuff like that. But also, what the inverse axioms say, I think, is also interesting with respect to commutativity. So let me actually look at 20 and 23 and just look at those together as far as giving you guys feedback and look at what some of you guys wrote. So one thing I wanted to point out is that as far as proving that things are a group, when it comes to let's look at the identity and inverse axioms first, even though those are a little bit more complicated in a sense because the quantification is more complicated. Associativity, the quantification is just for all ways you can pick 3 things in the group, blah, blah, blah. Whereas for identity, you've got there exists a special thing in the group such that for all things something happens. And inverses is for everything in the group, there is a corresponding thing that does something. So for identity, for example, if you're going to prove there exists, then somehow in your proof there has to be an idea of what that special thing is that's the identity, right? I have to be able to look at your proof and say, oh, that's what the identity is. That's what the special E and G is that works for every A. Where by works, we mean this, and we'll come back to that in a second. But just looking at, for example, let's try to memorize who's in the group, right? Jess and Morgan and Carrie. Like, what you guys wrote for identity, what they wrote for identity, makes it clear, even though they didn't say this explicitly, that like this is their identity, right? Everybody figured out what the identity was in this particular group. And this is a pretty good explanation of what makes that thing the identity. If we took an arbitrary thing and we added that to it, then we would get the thing, right? That's what the identity axiom says, right? But there's actually a tiny bit more that I wanted to just call your attention to, and that is that that it actually has 2 directions to it, right? It doesn't just say that A times the identity is A. It also says that also the identity times A is A. And I tend to forget about this, but there are actually 2 things that we should check. One is this A times the identity bit, and that's what you guys actually did check here. You had like A plus the, I mean, it's not times, it's plus in this case, but A plus the identity. And I don't know that anybody thought to check them both ways, okay? So also, like problem 21, we can jump in with that here because even though problem 21 said choose an axiom and show that it works, actually the axiom you had to choose was the identity axiom because associativity I told you not to check because it's miserable. I stand by that. And then the third axiom was inverses, and that doesn't hold for all the 2x2 matrices. So for problem 21, you were going to end up showing that the identity axiom, the second axiom holds. And so again, like I said, when I look at what you wrote, I'm going to be able to see what you believe is the identity, and then there's going to be a proof of that. And so here again, there should have been, it should have been that you think about like A times E and E times A when you prove something for the identity. When you prove that that thing really is the identity. And I don't think anybody actually did that. So notation here is a little confusing, but I can tell that this is still like an A times E kind of thing. So that is something that we should just remember to look out for with respect to that. Whenever we show that the, like in 21 here, whenever we show that that something is an identity, we have to consider multiplication in both orders, because, of course, it's because we're not assuming that A times E and E times A are the same thing. And in fact, you might be like, yeah, well, we know they're really the same thing. Well, in fact, in the case of matrix multiplication, they're not in general the same thing, because matrix multiplication is not commutative. Anyway, so that was for like 20 and 23. Okay, that was like just looking at the identity property. And then there's the existence of inverses for 20 and 23. And so how do you know, so how do you prove this if you're proving something's a group? Well, you need to start with that arbitrary thing in the group and show that you can add something to it to get your identity. So one thing to notice right away is we need to think about the identity axiom first so that we know that there is an identity and we know what it is. And then after that, you can deal with the existence of inverses, like for 20 and 23. So just looking at that stuff, 20 was about adding matrices. And I think, let's see, I think this is Victoria and Catherine and Zach. I think you guys, this is sort of confusing notationally because there's like R's and I don't know, instead of just A, B, C, D or something. But either way, I think that maybe this expression came from thinking about like multiplicative inverses. I'm not really sure. But, in a sense, it doesn't matter, right? I mean, the point is that like whatever this is, if it's right or it's wrong, you should be showing me why you believe that it's really the inverse under addition. And what that would mean is that if we add this thing, we're going to get the identity if we add it to A, right? So we would want this to actually be our identity, which was that. So just jumping around here for problem 20. So I'm just thinking about inverses for 20 and 23 right now. For inverses for problem 20, well, okay, so I guess you gave sort of a general explanation of why we should believe there's an inverse, right? But we really want to start with, right, if we're following the quantifiers to write a proof, we want to start with an arbitrary thing and just show what its inverse is. So that arbitrary thing in the group might be A, B, C, D, or something like that. So that, that should be something that we can do to write a proof like that. So it could be that, starting with, well, actually, I'm starting to wonder, like, for problem 20, did anybody actually do that? Did anybody explicitly write the inverse and say, to prove that there's an inverse, did anybody actually write down what the inverse is of this arbitrary thing? I'm sure you could, right? And that would give you a pretty quick proof. Like, you just want to show that if I write down a matrix that's the inverse of this, and I add it to A, B, C, D in either order, then I get my identity 0, 0, 0. So if we were in class, I'd kind of have a little conversation with you guys, and I'm sure you could do that. But I'll leave it to you to decide if you feel comfortable writing a proof that something satisfies that identity axiom. Right, but again, just to emphasize, that very beginning of the axiom shows up as your, let A, B, C, D be in M2R. Right, as soon as you say that, then you just want to show, hey, this is the thing you would add to it in either order to get your identity, 0, 0, 0. So lastly, I want to say something about the associativity for 20 and 23. Like they asked you to show associativity. Now I want to make a brief observation about what one group did for problem 23. And the group that I'm specifically interested in is, let me see, for problem 23, I want to highlight a couple things. I just have to remember which group I am thinking of for problem 23. So for associativity, so this is not the property of associativity, right? So for associativity, what we need to start out with is 3 matrices, and we know that because the axiom says for all A, B, C, and G. So we're going to have 3 objects in the group that we're talking about. And there was one group that said, for associativity, they said multiplication is associative. So they didn't really say anything, but that's kind of interesting in and of itself because it's true that multiplying matrices is associative. And if you believe that, then that carries over if you're just dealing with these special matrices, right? If multiplying any matrices together obeys associativity, then multiplying just ones that look like that will. So if we're willing to believe that associativity is something that would apply to all matrices, then that's enough to explain why it applies to just our special matrices. But if you actually wanted to prove that our special matrices are associative, then Ashley and Shihan's group here, they have an explanation of why that is, right? They actually tried, and I think actually going through the steps is actually worthwhile, even though it's kind of drudgerous, because it sort of brings you to terms with what associativity is really about, right? It's about grouping, right, with parentheses. Well, yeah, but it's actually really about the order in which you do things, right? There's an important way to think about associativity in terms of the order in which things happen. And this is worthwhile to think about partly because, your students will, I think, get confused sometimes about associativity and commutativity. And I say that because I've had many students in this class get confused about associativity versus commutativity. And it's hard to understand where the confusion comes from until you notice that like associativity is not just about parentheses, it's about an order, right? It's about like, well, if you multiply these two things first, right, and then you multiply that by EF minus FE, or if you multiply these two things first, right? Those are really the two differences. So you guys did a great job of showing exactly what you want to show in order to believe that the things are actually associative, right? And of course, they're also showing us down here why, like for example, that number is really going to have to be the same as that number. So that's really nice. So just to recap, for associative, you should definitely have 3 matrices to play with. And I think that's all I want to say about 20 and 23 as far as what's interesting. Usually associativity is not nice to check. Although, I got to be honest with you, like I suppose even though I said it would be miserable to check for 2x2 matrices, it's not really any worse than what Ashley and Shihan did to check it for just the guys in problem 23. But in any case, for 21, we talked about that one with the identity property a little bit already. And then 22 is about like, well, what about what doesn't hold? It turns out what doesn't hold is inverses. So why is it that inverses don't hold for 2x2 matrices? I think some of you guys just pointed out, well, the 0 matrix is not going to have an inverse. I don't think that anybody for problem 22 actually went to like the general formula for a matrix inverse and said like, oh, this formula might not work. Actually, no, you guys did. I'm sorry. So you guys actually said exactly when, given that this is the formula for the inverse, when it's actually not gonna work, when AD minus BC is 0. So this gives a nice characterization. Certainly if A and D and B and C are all 0, so that you're dealing with the 0 matrix, then you've got this situation like Victoria and Catherine and Zach pointed out, where like that guy is going to have AD minus BC equals 0. Okay, and then Ashley and Shihan sort of pointed out more generally, like whenever you have whenever you have AD minus BC being 0, you're not going to have an inverse, right? So all the 2 by 2 matrices do not form a group because inverses don't work. You don't. I shouldn't say inverses don't work. You don't have the existence of inverses under multiplication, but everything else does work, meaning all 2 other axioms. Anyway, so I'm asking you guys to think about these problems for a couple reasons. One is matrices are on the Praxis test, and so I like to build in some review of matrices to the class, just in general. Okay, so I bet you didn't expect to hear me say Praxis in this video, but there it is. And then the other reason is that doing the checking the axioms for matrices really helps you work through thinking about exactly what the axioms say, like we saw with associativity. So I really like that. I hope you did too. And then lastly, for problem 24 is a little bit of a shift of gears. I asked you guys to make a table for the operation of addition, and I think that you guys all did that totally right. Okay, so you have a table that looks like this, and you have a table that looks like this, and I know I looked at all these before, and I don't recall seeing anything that looked at all off. And that's great. I usually actually get some questions in class about exactly what I mean by a table. So I'm glad you guys were able to talk about that and be successful in making that table. And then one thing I think is cool is that you can see some of the axioms in the table. And so I mentioned in my last discussion video, I think, that what you don't want to do is, well, I mean, you can do this, but we can just say, well, how do we know that there's an identity? Well, 0 is the identity, right? That's the first thing you need to do is say what the identity is. And how do we see that 0 is the identity? It just says because a plus 0 is a, right? So remember again, like we also need to think about 0 plus a, although that's not really a big point at this stage. But also, like, what I really want to emphasize is, like, what do we see in the table that shows us that a is the identity? Like, what does that look like visually? And I think that you guys did a pretty good. Okay, I have no idea what I just did. Oh no. Okay. All right. It's all good. Situations like this always make me feel a little old. It's like, okay, just go back to where you came from, please. Okay, maybe I should. All right. Okay, that nightmare's over. At least there's no spiders crawling on me this time. Okay, yes. I want to finish this up, but yeah. So if you look at what Zach and Victoria and Catherine wrote, right, they give a very visual description of every row and column has a 0 in it, right? And that's true. Like, see, I get to highlight on what they wrote. I feel very special, right? Every the fact that there's a 0 in every I need that one too, in every row and every column, right? Now, actually, they said row and column, right? Isn't that interesting? Why do we need both? It's because if I'm looking at the rows, then I'm thinking of taking something, meaning like if I look at each row being my A, then I'm thinking, okay, can I add something to A to get the identity, right? So like if I see there's a 0 here, then I'm like, oh, yep. Okay, maybe that's a bad example. Let's say here, right? That 0 shows me that, 4 does indeed have a thing, namely 2, such that 4 plus 2 is 0. So that's kind of the a plus 0 angle on it. But if you look at the column as being a, right, then I would say, 5 does have something, namely 1 plus 5 gives me, right? So that's kind of asking, is there something I can add? Sorry, that would be like a minus a, right? That would be like something I can add to 5. Sorry, I just wrote the same thing twice. I'm trying to say one thing and think something else. Okay, so if I look at it row-wise, I'm picking an A, and then I'm saying, is there, in fact, a minus A that I can add to it that'll give me 0, right? That's what I'm looking for. Whereas when I look at the column first, I'm thinking, okay, the column being like the second operand of my addition. I want to know, like, is there something that I can add to A to get 0? So seeing those zeros in the column shows me that, yeah, there's something I can add to A to get 0. Anyway, I've made a big deal out of this and it's taken too long. But the point is, you want to look at row and column because it reflects that that part of the inverse axiom where you're looking at both A star B and B star A. Okay. All right, and then I think that associativity, I said, is not very visual, but identity you can see because, first of all, it says the first row and column show that 0 is the identity element. So they're looking at the first row and the first column in all this. So that would be like these guys, right? So what do you see there that shows you 0 is the identity, right? If you read their description, it just says adding 0 results in the same element, which is just a statement of what it means for 0 to be the identity. So what does it really what is it really that you see? Well, what you really see is that the headers are kind of like repeated in that row, right? It's kind of like if you ordered the elements of Z6 so that when you made the headers, you went 0, 1, 2, 3, 4, 5, then that's what you see in row 1 is 0, 1, 2, 3, 4, 5, and in column 1, 0, 1, 2, 3, 4, 5. So it's kind of like that you see those two headers reflected that tells you like, oh yeah, that's showing me that the identity that's there really is, really is this thing, right? If it was row 1 and column 1, then it must have been the zeros. It's the identity. So that's how you can see visually these properties of those two axioms, except for associativity. I don't think there's any way you can do associativity. All right, that's about it. I'll post this, and then pretty soon we will look at the next bunch of problems. But you guys did well. I'm pretty happy. I hope you had fun thinking about the axioms, and you kind of get your hands dirty multiplying matrices together. It really kind of gets you thinking about, how the three group axioms, what they're really saying about multiplying things together or adding things together and how those work.